Is Juliet here? Yeah.
Yeah, I'm here.
You're just quiet.
I am eating breakfast because it is still breakfast time here.
Yeah.
You're welcome to the West Coast. Exactly.
Yeah.
No, I was like, I can't believe you guys are waking up at 8 every time to do this.
This is the
Like,
thing.
I
hope
think if
people
it had not been
appreciate.
time, I probably would have faltered a little bit. Oh, there we go. I got the link. I'll put it in.
So I think YouTube is live, and
Yeah,
I think I will. Actually, I'm going to email someone the slides. Who's got the most band? I mean, the most. Let's see. Let me mail, and I will send it to Taylor.
yeah, I can do it.
Okay. And I have to remember your
Taylor.dupuy@gmail or
Taylor
Taylor@UVM.
at Gmail. It's Gmail because that's what I just remembered right now.
Yeah.
I can spell Gmail. UVM is tricky. Okay, good. So if I'm not mistaken, the question is the screen share, which I need to, it's pause. So let me resume share. And I think right now, the question now is what you can see on the screen, and can you see the, great, can you see the screen share?
I can see the screen share. I can see your pseudo lectures and then the algebraic geometry. Why don't you try flipping a slide?
Great. Good.
I cannot see you flipping anything. So.
Oh no, that's not good then. Okay.
Yeah.
Better?
So
By changing.
Try again. Yeah, now I can see you flip.
Good.
Wait, try. It's a little choppy. Wait. I see one of them flip, but the other one doesn't.
You're watching
now
20 seconds later.
Now they're both flipping. Okay.
Okay, good. I'm thinking this is good. I'm guessing either Taylor is watching on YouTube, in which case he's 20 seconds late, or he's just very slow today.
I'm here, and there's only 31, so I think we should wait like 2 minutes or something.
And you can post the slides then if you are.
What Agnes and Wags are, or
I think it's a soft start today too. So I wanted like the math will be.
Okay, great.
On. Let's see. Okay, so I think maybe I'll declare victory and start, and with a soft start, and then we'll go, and the math wise. Oh, there's Jonathan. Great. Okay, good. Okay, so I'm trying a few new things out today. Obviously, this is the last pseudo lecture of the series, and the slides. I think Taylor will post the PDF somewhere, maybe Zulip, but they're not going to be updating because I'm using GoodNotes and trying something different. So this is again the last lecture of the series. And what I want to do is just describe where we are, what we've done, and what could come next. And then I want to do, of course, a good amount of new math rather than just tie things up. So I'll try to say things. I've chosen things that maybe will help tie things up with a bit of a bow. So maybe the first thing I want to say is that non-mathematically what we've done, which I remind myself of every week or so, just to remind myself why I'm doing this thing, which is around different parts of the world, different times, but for us around March, COVID shut things down pretty massively, and we're still not, we've been knocked down and not really in the US really back up yet. And so the idea was to just sort of in spite of COVID or despite COVID to try something new, and rather than simply say things suck, to try to take advantage of the situation and the fact that people are stuck at home, and to try something of value that we might not otherwise do. And so in particular, it has been unpolished. It's been sort of, I've learned a lot while doing this, and it's but I feel like the excuse for imperfection that COVID gives us means that we can really try a lot of new things, and they don't have to work the first time, but they might work the second or third. And so, so one reason I'm really glad I did this is that at a time when it's easy to just say, like, there are a lot of people going through a lot of difficult things and things are kind of tough, being surrounded by people, even virtually, who are who are doing remarkable things in different ways in a difficult time is really energizing. So it's given me way more energy than I thought. I feel, in a perverse way, happier with how the world is going than before this started. And in particular, the participants who maybe surprised me, because I did not expect to see this, is that a lot of smart people with day jobs started, but really said really interesting things on Zulip. And it was really impressive to see how people who's I would have thought would have been somehow rusty seemed to really just be able to figure things out. And also, this was less of a surprise that people from other fields of mathematics have really interesting things to say. That's actually tell that I've learned new things from them, and it reinforces in my mind that things aren't really knowledge isn't isolated, and everything is connected. And also, the first-time learners who are kind of on their own, but learning with each other and learning how to think for the first time. And then finally, the people who know a lot already, but what they're giving are points of view and comments that make things clearer to other people and even to me. And then I think the people I really want to thank, especially on top of everything, who made this happen, were the Shepherds. So thank you very much to all of you who've done different things in different ways to make this really work. And I think probably the participants have no idea how important it is. And if people are trying anything like this in the future, and one lesson is that it's really valuable. It's unbelievably valuable to have a bunch of, I don't even know how to describe the group, because they're like at different career stages, they know different things, they contribute different things. But this is the thing which really makes it from one crank shouting on a soapbox into the void into something which could actually work. Okay. Also, I want to thank explicitly. So Zulip is a company, and so they ideally will make money, but they are probably already making money, and they are they're giving us access to this in large numbers, which would cost money, for free, because they think it's worthwhile. And I just wanted to, they're not watching, so they have no idea I'm thanking them, but that makes it even maybe better and they're started by some math people who are mathy and went on to do interesting things, like many of the people who are watching, who are not professional research mathematicians. So, and also I want to thank Eric Domain for explaining co-author, and Siddharth Mahandraker, who set up our co-author installation, which I would not have been able to do at all. It took a lot of time. Okay, and then last thing I want to say before we get to math is sort of, some people have asked me sort of, what's in it for you? Why are you spending your time on this? And so I made the reason I was very happy about doing this is not just partially the getting energy out of other people, somewhat vampirically, by just being surrounded by people who I'm very impressed by, but also I could try things out with a forgiving audience, because you knew, I guess, I owed you nothing and I had no time, and it meant I could try a lot of things out. And I think it's this issue of that there's no such thing as a stupid question. The willingness to do things and get things wrong that I think professional mathematicians gradually know, and maybe people coming into grad school don't yet. And so the other thing is, the things I wanted to experiment on that I might as well tell people about, because I think other people are trying to do the same thing, is the question is not just think in a theoretical sense how things can work, but actually try things out, which is how to reach people. And I think this really means where the talent is in the world is not in all the, somehow people have to know and then get access. It should be free. And ideally you should reach into as many places as possible. Whether things should be synchronous or asynchronous, I think synchronous is better, but asynchronous is necessary, and there are pluses for both. And also the thing which I really want to figure out is you can't learn things passively, as everyone here knows. And how do you set up a system where you kind of automatically fall into, like, where you wake up and fall out of bed and you're already thinking actively, not just watching videos at 1.5 speed and thinking you're learning something. But maybe you're watching at 1.5 speed and, well, okay, well then slow it down. And then the other things that were worth describing are how to present remotely, and I can try things out. I learn things. This is the first time I've tried to do things online of this sort. Even today, I'm trying new technology. And also the videos, those are publicly available. Anyone can use it. And I'm actually experimenting this fall in an official class where people can watch it and then we talk on co-author. So it's just a chance to set up future experiments. And so so where to from here? So in terms of AGITTOC itself, I could completely imagine, but I'm not certain, far from sold, that maybe continuing with a follow-up edition, but it wouldn't be any time before Christmas break here because things are rather hectic and will remain hectic, partially for COVID reasons as we sort of scramble to make things work. I also want to, over the next while, even after today, go on to Zulip and now gradually collect lessons that are learned, since especially people made a bunch of suggestions on how this could work with making groups and things like that. And you may think you're saying things into the void, but I've read some and I want to read them all and I want to pass those on. And then for other courses and things like this, I hope people continue to experiment. Right now, Karen Kalaya is giving a number theory course. So you can, I guess, Google that or ask someone about that. And there are other courses coming that if you pester them, hopefully they will be very public. And like, for example, Jared Alper on stacks. I know Daniel Litt's doing a telecohomology right now. So just, yeah, the more people, the better. And now I want to finally get on to math and get on to new math. But first, just on to math, to say what we've done to try to describe the point of view at the beginning and how we got there, how we were getting there. So the theme is going to be how algebra is to connect algebra and geometry, to think about algebra geometrically and geometry algebraically. So maybe the long-term plan is to get pictures of algebraic notions and not just hand-wavy pictures, but things that have implicit rigorous content. So in order to make that make sense, we had to first figure out what we meant by geometric content and what we mean by some sort of space. And so what's a geometric space, which led us fairly early on to the notion of a locally ringed space, or a ring space that happened to be locally ringed, maybe I should put it that way, with some sort of nice geometric local model, and then you plug and play whatever local model you want to invent different kinds of useful geometric spaces. Okay, but that meant that you had to have a that meant you had to have a, let's see, they're great. You have to have a topological space and a sheaf of functions. So that requires, and it's good dividing topological space into set with topology, but then we need to know what really sheaves were. And I guess the question of why is a sheaf is something I hope you have some appreciation of, although maybe not fully, that this is a good way to package what a geometric space is going to be. And then to think correctly about all of this, we had to go one step further back and learn how to think in a clean sense, because that would tell us what to define and it would tell us how to set things up the right way, which is one of Grothendieck's lessons, that if you know what you're looking for, you can set things up the right way and things become very clean later on, even though you don't know how. And then that lets us finally get to where we are, which is to have a bunch of algebraic notions that we can make that we can think of geometrically. Okay, so that's the, and so I also heard, so Terry Tao has this view of algebraic geometry, or his description, Cliff Notes view of how to think about it, which I feel like when non-algebraic geometers talk about it, often there's like more distance and better perspective sometimes. So so it's something which you have the algebra part, which is about rings and ideals, and then so I guess geometry is the ambient space in which we're working. So it captures the algebra, but then because you've added nilpotents, in effect you're adding derivatives and analysis. So this idea of being able to work to first and second order and higher order, it lets you think about tangent vectors and derivatives and connections. That's in some sense that's analysis. And then the topology comes into it because the algebra specs are the local picture, and how you glue them together is a local to global. There's a local to global issue, and then you can bring into topological tools like homology, and you can understand the topological spaces by cutting them up into, let me see, is this going to work easily? Yeah, pretty easily. That's not what I wanted. And so you have these things which are nice and local, but then by how you glue them together, you get some global information. So that's a quick big picture, which is better for me to give at the end of the 14 lectures than at the beginning. And now I want to say new things. So let me see how are we doing. It's about 8:20, which is roughly where I want it to be. And so, okay, so that was the meta conclusion. But now I want to actually end with some interesting math. And so the last topic I wanted to talk about were things to do with images of morphisms of varieties and schemes. And so the first such topic, the start of this is going to be the fundamental theorem of elimination theory. This is one of the I think it's okay to say it's one of the major achievements of 19th century mathematics, or at least one of the central topics of a big chunk of it. I wouldn't necessarily place it in the top 10, but maybe in the top 20. And so to motivate this question, let me ask you something which you would have, which you have asked yourself, things like this before, which is if I give you a bunch of, for example, linear equations, and like here are 4 linear equations, 4 unknowns, and you want to know if they have a common solution. And maybe the first thing you'll say is that obviously they do, because zeros, but you have a bunch of zeros. All zeros definitely work. So the question when asked is do they have linear algebra is somehow about the question, do they have a common non-trivial solution? And how do you check that? Well, you could either just try to solve it, or we have this, you could just try to solve it, or you could invent the determinant and check whether the determinant of the coefficients is 0. And so let me just take a step back and point out what we're doing. You could have just gone ahead and figured it out, or you have an algebraic condition that for the coefficients of, I guess the ones are invisible, as ones tend to be, of the coefficients that if they satisfy an algebraic relation, which is the determinant, then there is a non-trivial solution and not otherwise. So that's the thing I would like to extract. Okay, so now the more general statement I'll say is, okay, so not just degree 1, because we already know about determinants, but if you have a bunch of homogeneous equations in, say, n variables, and you want to ask if they have a common 0, and as before, I want it to be a common non-trivial 0. And so this is naturally, I think, like if I give you a bunch of degree 2 equations and 4 variables, you can completely imagine that you would expect or hope that there'll be some algebraic way of describing when they have solutions. And ideally, it would be algorithmic. And maybe I feel like there's a part of the 20th century where things bifurcated or trifurcated in mathematics, where in the 19th century, you would think algorithmically and I don't even know what to call it, the non-algorithmic way, proof rigorously without algorithms, like things like there exists rather than how do you find it. Somehow you do both at the same time. And then briefly you would also do math at the same time as you did physics, and people would know both. But then we got pure and everyone specialized in the early part of the 20th century, and then everyone knew different things. And now we're one happy family again. And we realize that if things are algorithmically understandable, it means they're theoretically understandable, and vice versa often. So, okay, so the question is that you have a bunch of equations. How do you tell if they have a common 0? First, you should hope that there's some algebraic way of saying it. It shouldn't be transcendental. Secondly, you should even hope there's like a beautiful algebraic way of describing it. So that's what we want to do. And maybe another thing I would say is, in the course of doing this, you'll notice all we need to do to make this work is to understand determinants well. So it's also part of this continuing mathematical theme that there's like linear algebra, first order things, and then harder questions you try to turn into linear algebra whenever possible. Okay, another example that you may have seen, which you can say in elementary ways. I will say that everything I'm going to say could also be all said in elementary ways. But if you have 2 polynomials, one of degree m and one of degree n, and you want to know if they have a common root, and I'll make them monic, then there's this thing called the resultant. Let's see if I remember to, no, I forgot to write that down. So this is called a resultant. And but it is a determinant. That's maybe the lesson is it is a determinant that tells you whether they have a common root. And the resultant is you take the coefficients of the first polynomial and you write them down and you sort of put them, a bunch of copies of them, n copies of them in a little parallelogram. And then you do the same with the second polynomial of degree n, and you put them in a parallelogram m times. And there's like a very easy reason why the statement is the same as that statement. I'm not going to describe it now, but you get this nice formula. And so that's really useful. And as a special case, when one is the derivative of the other, you get the discriminant of a polynomial. It tells you if a polynomial has a repeated root, which is the same as if the function and its derivative have a common zero. Great. And then, one thing I should say though is everything I'm talking about is I said we're talking about homogeneous polynomials, and there are no homogeneous polynomials here. There are no homogeneous polynomials here. So where are they? Secretly, they're here because you could put you could add a second variable here, but I'll leave that for later. Okay, so now I'm ready to tell you the fundamental theorem of elimination theory, which is in modern language the following thing. So I guess, well, I don't think he would necessarily say this, but I'll say this because he might be muted now. Jonathan would be upset because he'd want to use the value criterion of properness to prove the fundamental theorem of elimination theory. But I'm hoping this will satisfy him as a reasonable thing to do. So great. So so the statement is this. I'm going to take, okay, this is the wrong modern, this hides what's going on, but let me just say it in the language we have, which you take projective space, let me increase my size and change my color. So you take projective space over your ring A and you're mapping to spec A. And the statement is that it sends closed subsets to closed subsets. So this means, this is the definition of, I guess, a closed map. It's closed to closed. And then what this, furthermore, because if this is true for every single A, then you can quickly show that this remains true by sorry, there's a little m there. If you zoom in, you see a little m. That's because if you really feel like just dealing with, if you're following along thinking only in terms of varieties, this works just fine if you were in variety land as well. And then it's a closed map, but then you could because after base change to a different ring, it looks essentially the same thing, just with a different A. This means that not only it stays closed after any base change. So it's universally closed. And what that means is, what that implies that projective schemes are proper because they are, the definition of proper was separated, which we already checked last time, that projective space is separated. It should be finite type, which we already checked last time. And the last thing we didn't check yet, and now we have, is that it's universally closed. So that you could describe it this way as well. So that's the statement, and now I'm going to prove it. So here's how. So let me just restate the question, and I'm going to restate it a few times, and then at some point the proof will be done. So we want to show that the image of a closed subset of projective space is going to be closed. So how do we think about closed subsets from projective space? Well, they're cut out by a bunch of equations. We have the bijection between, we have the incidence reversing bijection between, well, I should say this, well, let me just say that any closed subset is cut out by a bunch of equations. So I'm going to take inside this proj the bunch of homogeneous equations we have and consider this. And I'm wondering, is the image of this downstairs going to be closed? And just because I have a graded ring, I want to give it a name. So I'm going to call the graded ring S, because that's what we call, S is short for graded in Ukrainian. So we take S sub dot, and that's our graded ring. And so the question, so I'm going to ask, we want to know what the image of this thing is, a closed subset of projective space. And we're wondering about its image down in spec A. So let's ask about whether a certain point is in its image. So take a point of spec A, and this is the corresponds to prime ideal, where that's meant to be a different font, the factor font. And let me just give K or the name for the residue field. And as a reminder, that's just you take the local ring and mod out by P, or take the integral domain, take its fraction field. It's the same thing. And so the question I'm going to ask is, given this map, and I'm wondering if there's a point down here, which is spec K mapped in this way, is it in the image? Well, what do I need to do? I need to take a look upstairs and look at the ring where I'm I'm modding out by P, or I'm tensoring with K. And my question is over spec K, I've got a bunch of equations. So I'm not just over a field, I have a bunch of equations in projective space. Do they have a common non-trivial zero? So this is back, even when we're talking about rings, my question is just about things over a field. Okay, so my question is P in the image of pi? And so in other words, so translation, it's in the image if inside spec, we're talking about proj, but if in spec we want to check if they have a non-trivial solution. In other words, this comes back to our statement of we want to ask if there's a solution besides 0, 0, 0, 0, 0. If there's a solution besides 0, 0, 0, 0, then there's a solution in projective space. The question we're asking is, it's in the image if and only if these equations have a non-trivial solution. Well, that means that when I set G1, G2, and so forth equals 0, I want something not just the origin, which is cut out by x naught through xn. And now that I have something with vanishing loci, with v's, we have our bijection with radical ideals. So that means that the radical of G1, G2, and so forth, I've reversed the inclusions, does not include all these. I should maybe put equivalences here. So I want this radical ideal not to include this radical ideal. But I should say this radical ideal this ideal was already radical. So the question we're asking is the maximal ideal, this thing not contained in that? But the ideal is generated by by n+1 things. So we're just asking that each of the elements not be in the radical of this ideal. But the definition of radical means that some power is in the ideal itself. So we want to check that there's not some power of x naught or x1 or all the way to xm inside this ideal. And I guess we could take the same power. I should make that look like an m instead. But that's really the same as saying that there's no degree n. This is a different n. That's an m. So if there's no finite, for all m, the mth powers are not inside here. It means that for some bigger thing, no degree capital N polynomial is inside here, because otherwise any degree n monomial in these variables would have one of the terms that appear to degree at least m. Okay, so just to make sure you know I'm not cheating, let me just go back and say it quickly. The question is P in the image, which means do the polynomials have a non-trivial solution, which is, that's a restatement, which corresponds to a statement about radical ideals, which we want, and that we want to get rid of the radical. One of them already is radical. So the question then is, if the maximal ideal is not contained in this radical, that's the same as no power of the maximal ideal is contained in the original ideal. Okay. So that, just to restate that again, this means that the mth, I should have called that a capital N. That's okay. Now it's a lowercase m. This means that the entire nth part of the graded ring should not be inside, contained inside the ideal determined by the G's. Okay, but what is the ideal? Uh-oh, I seem to have switched my, yes, I've switched my sides. Great. So what this means is, the question we need to ask, what this means is that for any degree m, there's some degree m thing which is not in the ideal. And what are the things that are in the ideal? Well, they're multiples of G1 plus multiples of G2 plus ... So the degree m polynomials are not contained in this ideal if and only if multiples of G1 plus multiples of G2 and so forth is not all of, you can't get all degree M polynomials in that way. And so in other words, if you take polynomials of degree M minus G1 and M minus G2 and so forth, and you take this one multiplied by G1, this one multiplied by G2 and so forth and add them together, then you get a degree M polynomial. This is a linear map from a vector space, a vector space over our field to another vector space over our field, which is basically just, once again, take this vector space, just multiply it by this polynomial G1, take this one, take this corresponding thing, multiply something in G2. So this is just linear algebra. So the statement is that for all M, this is never surjective. This linear map is never surjective. So this now is linear algebra. The matrix of this this matrix, which is never full rank. And what is this matrix? It is whatever that dimension is, some finite dimension. That's there we go. I wrote down this big matrix, but the number of rows is this dimension. And the statement is it's never full rank. Well, how do you know if it's never full rank? Well, now we're just talking about linear algebra. A matrix is not full rank if whenever you take all the determinants, whenever you take all sort of determinants that fit inside there, set them all equal to, if they're all equal to 0, then it's not full rank. If anyone is non-zero, it's full rank. That's so that means for every M, so in other words, the statement that P is in the image means that you have a bunch of determinants or 0 for each M. Otherwise, I could just do it all at the same time. You have infinitely many determinants equal 0. So what we just said is P is in the image if and only if this infinite family of equations is 0. It's the vanishing locus of a bunch of determinants. And so our answer, finally, when you go all the way back, is you just take, this gives you, maybe it's not a satisfactory recipe because you have infinitely many polynomials, and I agree that's not so, this is not so perfect, but I want it, but at least it's rigorous, that you have infinitely many determinants. All the coefficients were things you write down, like what this linear map was in terms of the coefficients of our polynomials, and we just get the so we get actual equations in A that came out of determinants that will cut out what the image is. So that is the end. Okay, so if this were more conversational, I would stop and then discuss every step and see what questions people have. And now I feel bad that I can't exactly do that, but I at least want to say that nothing. I did not cheat. If you're wondering if I was cheating, I don't mind cheating, but I usually will prefer to admit when I am doing that. Great. So that means we now know this. Oh, maybe there are things I should say. You might think I'm cheating if you worry that this is an infinite matrix. Like I didn't say, I very carefully did not say how many equations I had. There could be infinite. It looks like it's countably infinite. I don't even care about that. That's just because I could have infinitely many equations and nothing goes wrong. It's true this matrix becomes finite by infinite, but that's okay. Everything works just fine because I was already paying the price of having infinitely many determinants. So I can't, you can't complain about that now. Okay, but it is true, I should say, that you'd want to know that you don't need to check infinitely many determinants, but we're not going to worry about that because we did it. Okay, so I mean, I almost want to check if the shepherds want to ask something, or anyone wants to ask something, because any question they would ask is something others would like to ask. But the shepherds can just jump in whenever they feel like anyway. And now let me ask the question of what if the equations were not homogeneous? When they are homogeneous, we now have a way, if you have, I don't know, 75 quadrics and 3 variables, of seeing when they have a common root, and there's some algebraic condition on the coefficients. So what happens if they're not homogeneous? Well, something more complicated happens for completely unsurprising reasons that you know very well. And so here's as a sample question, and I'll do it. I'll start with linear algebra because, as before, it's just going to be nothing more than linear algebra done right. If I said I've got 2 linear equations and 2 unknowns, there seem to be a lot of unknowns, but what I really mean is that x and y are the unknowns. And what's the condition on the coefficients so that they have a common root? And you already know how to answer such a question, of course. And what you consider you'd be forced to think about various cases. And depending on how you thought about it, you would choose different kinds of cases. But just for example, a very reasonable way to go would be say, okay, if a is not 0, then I could divide by a, and then x is something like this, and I could substitute, get rid of this x by using this equation, and blah, 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 and keep on going. Or if a is equal to 0, okay, then I could just forget that. And now then I'd go, okay, then I'd say, okay, well, what about d? Maybe d is 0 or not 0, and I have those cases. So I'd have a bunch of cases, and your final answer would involve a bunch of cases, and you wouldn't be shocked or surprised. And so the answer, maybe I want to do one more. Okay. Maybe there's an example I will do. Let me actually do an example now. Okay, no, I'll just wait. Okay, so how do I say what I mean by these cases? But the cases are all algebraic. If something equals 0, something is non-zero. And then you'll say, yes, if a is non-zero and d is, if this determinant is non-zero, if AE minus BD is non-zero, then it always has a common solution. However, if A and B and D and E are 0, and if A and B are 0 and C is non-zero, then it can't have a solution. Things like that you would say. And so the answer would be the following form. It's what's called a constructible set. So let me define it on a general topological space, which is you basically just have open sets and closed sets. It can't really hurt. And you could take complements and unions and intersections finitely often, and that'll describe some collection of subsets. And these are the ones that are called constructible. And that's what your answer is going to be. And fairly clearly in this case, you're going to have finitely many cases, and you'll be able to. And if you want the finitely many cases here, if you understand why that's true, and I know you do, then you could then show quickly that a set is constructible if and only if it's a finite, maybe I should say disjoint union, not that that matters either, of locally closed subsets. That's a different way of describing what it is. Okay, so hopefully that's not shocking, and it's not that this notion is something that you already knew about a long time ago. Okay, but Chevalet's theorem, which I'm going to say in a needlessly fancy way. Great. But so the case you might care about is you just have a map of varieties. But I'll say it, I might as well, because it can't really hurt. Well, it can hurt a little bit, but it's, but yeah, think of it like a vaccination. So suppose you have a finite type morphism in Noetherian schemes. What does that mean again? It just means locally it looks like spec A, and it's and there are only finitely many of them. I guess technically I only need low. Well, I'm not going to go there. Yeah, let me not worry about making my hypotheses super general. And so then under these hypotheses, the image of any constructible subset of X is a constructible subset of Y. And the case that really matters to us, perhaps in the initial question, is the image of all of X is going to be constructible because X is a constructible set. Or the image of every closed set's constructible, every open set's constructible. So that's what the theorem says, and that's what we're going to prove. And so what's behind this theorem? Let me just do let me reduce to the case, the affine case. So, and we can do that because so Y is a Noetherian scheme. So that means that Y is covered by finitely many spec of Noetherian rings. And if the image of X, or given a constructible subset of X, if the image is constructible in each of these finite things, it was constructible to begin with. So using this, we can reduce to the case where Y is affine. And then at that point, we have that if Y is affine, then X is the union of the preimage of Y is a union. And because it's a finite type morphism, it means that it's quasi-compact, which means that I can take finitely many opens. Each of these is spec of something finite type over A. And if the image of something of this is constructible, and the image of this is constructible, the image of this is constructible, and so forth, the image of everything together is the union, a finite union, and it's constructible too. maybe I should have said that slightly better. If I have a constructible subset of the whole space, then it's the image of the constructible bit in here and in here and in here and in here and in here. And that means, so if I deal with each of these cases separately and take the union, I win. So I might as well assume X and Y are both affine. And if so, what's the question now? Now, Y is a Noetherian ring. Y is spec A of the Noetherian ring. And X is finally generated over Y. That's the finite type. Mod some ideal. But any constructible set of a closed set is also a constructible set of this. So my new final question, well, not even my final question, is that affine space, that if I take affine space over my ring to spec of my ring, sends constructible to constructible. And maybe this reminds you of the fundamental theorem of elimination theory, which says projective things over a ring sends closed to closed. And although I didn't have any Noetherian conditions there. So that's what I want to prove. Now here's an example I should have given earlier about how to think about constructible subsets. So here is my map. Here's a map from C2 to C2. And so I really want you to secretly think of this as A2 over to A2, and the field doesn't even matter. And I want to send U comma V to U comma UV. And I could say, what ordered pairs can be written in this way? And the answer is, you can write it in this way. If whenever X is 0, then Y must be 0. So the image, when X is non-zero, you can get everything. But when X is 0, you just get that Y is 0. So you get this weird thing. It's not closed or open, but it is constructible. It's the union of this open subset with this closed subset. Or maybe I prefer to say it's the union of these two locally closed subsets. So that's an example. Another example, or really is that, or interpretation is, this is what's called elimination of quantifiers in mathematical logic. So if you have, and this is in the case where you're over an algebraically closed field, if you want to really use the, depending on how you want to say it. But it's, the example is, let's say over the complex numbers, you have something of like, there exists a solution to this such that for all that, for exists that. The fact that you can solve, you can algorithmically answer any question like that uses elimination of quantifiers, which is, and the elimination of quantifiers, this gets rid of the exists part of us. This deals with the existence part. Like there exists a solution of these linear equations where blah, blah, blah. That's a question about images of morphisms. Okay, and as another example, this is one I mentioned back, deliberately mentioned back in a very early one of our meetings, which is if you have 100 polynomials and fewer variables, such as 26, with rational coefficients, and if it has finitely many complex solutions, then how do you know you should guess that you're not going to have pi in one of the coordinates. Each coordinate of each solution is algebraic, as inside Q bar. So that's something which is going to come out of Chevalley. So use Chevalley for that. Okay, let's prove it. Okay, we want to prove that spec A, adjoin a whole bunch of variables to spec A, sends constructible sets to constructible sets. That's our plan. And so we can just add one variable at a time. So it suffices, because A adjoins some variables remains Noetherian in particular, that all we need to do is that if we have a Noetherian ring A, and just to be really clear, where's the Noetherianness is going to come into it at some point. Given a Noetherian ring A, then the spec of A adjoin T sends constructible sets to constructible sets. Okay, and now if I want to send constructible sets to constructible sets, it suffices to send closed sets to closed sets, if you think about what that means and why that's true, because a locally closed is one closed minus another closed. Maybe that's the best way to say it. So if you know closed sets go to closed sets, then constructible sets go to constructible sets. So okay, I will let you think about why that's true, but that's what we're going to do. We're going to show that closed sets go to constructible sets. Okay, so let's say I have a closed set. There's my closed set. It's Z or Z, depending on where you're watching this. And so this is you have a closed set. What's a closed set in affine space? Well, it's cut up by a bunch of polynomials, and these polynomials are just polynomials of one variable. So how hard can that be? So what I want to do is divide my. So I want to see where they have a common solution. In other words, for every field, every point in spec A, I want to check if that's a common solution. And I want to check, what I'll do is let me start to divide into two cases. My first case is where all these polynomials are of a certain degree. And so they have leading terms. They may not be monic. So what I want to do is I'm going to first check out the case where the leading coefficients are all non-zero. So really, so in other words, this is a distinguished open set where the product of the leading terms is non-zero. That's one way to put it. And I'm going to show that over this, I get something instructible. And I'll show separately that away from it, I get something instructible too. And that the rest of it is inductively easy, because if one of the I then break that into cases, and if one of the if they're not all non-zero, then at least one of them is zero. And if one of them is zero, then really I could consider the polynomial as being degree 1 less. So I can do some sort of induction with the degrees of these FIs. So these are all smaller degree cases. So inductively, we claim we're done. So now let's say leading coefficients are all non-zero. And if you want, I'm replacing A by this localization of A, because I'm just working over this distinguished open set. So now I'm really working in the case where Z is cut up by a bunch of monic polynomials. So there's so my monic. So I'm working over. I guess let me call B to be this localization, and I'm just to avoid confusion, I'm going to use B there. And so there's A1 over B. So it's and now I can compactify. Well, what does that mean? I can consider not A1 over B, but let me also consider. Let me choose a different color. Let me take P1 over B. So I've added in sort of something I might call infinity cross B. And the fact that it's monic means that if I look where V of F1 is 0, or F1 vanishes, it does not meet infinity. That's the thing maybe you should check, that it means all the roots. It's like you have a degree n polynomial, always has n roots with multiplicity. Maybe that's not so helpful. And so in other words, V of F1 is closed in P1 sub B. In other words, if you take the closure of this set inside this bigger space, you don't get any bigger set. Okay, what that means is that the locus, when I intersect each of these together, it means that the locus where all of them vanish was already closed inside P1 of B. So it's inside A1 of B, but it's closed, and it's closed in there obviously because it's cut out by some equations, but it's even closed in P1 of B. But now, by the fundamental theorem of elimination theory, the image of that closed locus in P1 of B is closed in spec B. And in particular, it is constructible. And that ends the proof of Chevallier's theorem. Great. And now let me end with a proof of something major that was left outstanding, which is the Nels-Dahlen-Satz. So I'm going to prove it in the form of Zoroski's lemma, and I'll remind you what that is. So this is something which I stated without proof, and I said we understand when we're older, but now we're older and wiser, and we can understand it So the question we're trying to show is the following thing, which is that suppose you have a field extension, and in this field extension, the E is an extension of F, and it's finally generated over F as an algebra. And then the Zoroski's lemma, which we wish to prove, says that E is finally generated over F as a vector space. In other words, it's a finite field extension. That's what I want to prove. And so now let me restate that. So great. So what does that mean that it's a finally generated over an algebra? It means, let me call the generators x1 through xn. So that means that E is f1 through xn modulo some ideal. But E is a field, so actually it's a maximal ideal. Now, what do we want to do? We want to show that that this field extension of F is a finite extension. So it would suffice to show that whenever we add each of the xi's one at a time, we get a finite extension at each stage. So the goal is that we want to show that x1 satisfies some polynomial relation over F, is algebraic. X1 is algebraic over F. Okay, so now let me just restate our situation, which is that spec of our spec of E, which is just a point. Let me draw. This is algebraic geometry, so I need to draw a picture. It's a point. But it's a closed point because it corresponds to maximal ideal. It's a closed point inside affine space over F. And affine space over F maps, I'm just going to forget all but the first variable. And that's A1 over F. And so by Chevalet's theorem, the image of this point under this map, this is a closed point, so it's constructible. Under this map is going to be a constructible subset of A1. So this constructible subset of A1, what are the constructible subsets of A1? Remember the topology of A1, which is just you have closed points and the generic point, that's the set. And the open sets are, the closed sets are just either everything or finitely many closed points. And the open sets are nothing or everything but finitely many closed points. Yeah, that makes it, yes. And so if you think about it a little bit, the only constructible sets are the open and closed, are sets that are open sets are constructible, the closed sets are constructible, and that's it. Or maybe think about it more and realize the only point that can be constructible is a closed point. So in other words, spec E maps to a closed point of A1. And what are the closed points of A1? I'm changing my X1 to a T deliberately so I don't get confused. That the closed point corresponds to an irreducible polynomial in F. And so, so what this means is that, okay, now here's where I'm going to use something. You can get around this, but as long as we've defined stuff, we might as well say it. I want to claim that F of X1 is 0 inside E. Why is that? Well, I do know that, so I know F, I could just say this quickly enough and you might believe me. But what I really need is that the scheme theoretic image of this point is this closed point. In other words, just because the set theoretic image is this doesn't mean that F of T is 0 when pulled back here. But this is reduced, and so the image is reduced. And so that means that F of X1 is actually 0, and bingo, we found our algebraic relation for X1. So we proved the Nullstellensatz, and that, I think nothing fancy happened, although maybe in the last half sentence you thought something fancy happened because I didn't say it in a way that could be faster. And so let me just sum up how this argument worked. Let me just go back here. What made it work? So what made it work was we start with the case of homogeneous equations because it is right. Because we start with homogeneous equations because it's simpler. And what do I mean by simpler? It's the closed go to close. Why are you not surprised by that? Well, you're not surprised because to go back maybe 2,000 years or maybe more, it's a fact that you want to work that when you ask questions about two lines always meeting, they always meet only once you work in projective space. Like you want to compactify to avoid the issue of parallel lines. So we've known, we've known that. But even earlier than that, the fundamental theorem of algebra says every degree n polynomial has n roots. But to make that precise, we need to work over an algebraically closed field. Oh, sure. But we also need to say with multiplicity. Sure, that's not a problem. But we also need to say that the leading term is not 0 in the polynomial, or translation, or you could instead say it has n roots if you include infinity. So you only get the nicely behaved answers when you have something compact or when you have homogeneous equations. So we got a nice, so that's the, so we have some, the determinant is an example about that because it looks like it's not about projective space. It looks like it's about affine space, but it's really about, it's really a question intersecting hyperplanes of projective space. And so the proof, like obviously the useful examples, and then the proof used fundamentally, maybe there's a feature of this proof I want to emphasize, which is that you're asking about solutions in projective space. And our proof used instead the affine cone over it. And we looked what we were looking, all of our activity in our proof involved this maximal ideal generated by x naught through xn. And this point of affine space is precisely the thing that you don't see in projection space yet. It's the thing which let us prove this theorem. So that's a feature that we end up looking at a point that was completely invisible from the point of view of affine space. It's not a generic point, so it's a different kind of thing. And then the trick, there's nothing more than linear algebra that made it work. And then with Chevalet's theorem, all we're doing again is we want to just use case analysis, and but we want to use it wisely, so we get in the case of linear algebra, it's easy to do case analysis, but we want to use it wisely, and we can take advantage of the fact that we already know about the fundamental theorem of elimination theory. And so we know what the answer is early in life, that it should be constructible sets. And so the one, for people who've seen other proofs of this, I should say, what makes this attack somewhat easier, it's that you're supposed to be adding a whole bunch of variables, and the reason it's better, you're supposed to add a whole bunch of variables, and if you add one at a time, the following argument works. If you try to do this all at once, you can think about what goes wrong in the rest of the argument. So it's essential that it's A1, not AN, and that's because when you take this P1 bundle, if you took AN and took a PN bundle, something weirder is going to happen here. So it's a fact that the fibers are one-dimensional for people who know language like this. And then you just have cases of, well, either that you wish you could work in the P1 bundle because you know the image of closed is closed, and the problem is that you would have things could meet what's going on here, and the trick of looking where the leading coefficients are non-zero, just like the trick when you have a degree n polynomial and you want to say it has n roots, the condition you want is that the leading coefficient is 1. That lets the set you're talking about be closed in the P1 cross B, P1 over B. And then you just use the fundamental theorem of elimination theory and you won. And then the Nullstellensatz, again, becomes something about images of, it sounds like a very field theoretic or algebra fact, but now it's become a geometric fact because that proof, there you go, there's a picture. It's something you can only understand with the picture. So even though geometrically you're setting a point to a point, you're thinking about it in terms of geometry, because the point is spec E is not just a point, it is inside, it naturally comes inside affine space because you've chosen algebra generators. Okay, so that is, let me make this go here and change the, so that's, now we're at, okay, 9:01. I slightly overshot, but not by very much. Thanks very much for taking part. I will still be on Zulip. I feel like this is the end of the last pseudo lecture, but not the end of trying stuff out. So I will talk to you hopefully on Zulip, and feel free, of course, to email me about stuff about this and other things. I should in advance promise to be slow on email, as everyone who's emailed me knows, but I usually manage to respond. Okay, thanks a lot, and I will see you hopefully in person at some point, all of you. Hopefully not at the same time, because there are too many of you. I will stop the recording. Thank you.